Hello, guys. My name is Adriana Valencia, and my partner is Alejandra Zapata. We created this project together for our fluid mechanics engineering class. Today, I'm going to talk to you about a couple of mechanical engineering concepts and teach you a little bit more about them. We will be discussing Bernoulli's equation and the flow rate equation to help any viewers have a better understanding of the concepts. We will start by teaching you the flow rate at point A. Point A is located at the top of our waterfall. Due to the water coming out of the pipe, we're able to calculate the flow rate. The flow rate Q is equal to VA. V is the velocity and A is the area of the pipe. The diameter of the pipe is 1/3 inch, so after doing some calculations, we're able to get the radius and get the area. The area is equal to 6 times 10 to negative 5 meters squared. The velocity is going to be the length of the pipe over the time it takes for the water to travel through it. The pipe is 2 meters long and it took approximately 3 seconds for the water to flow through it. Now we will solve for the flow rate by multiplying the area and velocity. The area is 6 times 10 to negative 5 meters squared, and the velocity is 0.66 meters per second. This ends up being 4 times 10 to negative 5 meters cubed over second, and then converting that to gallons per hour, it comes out to be 38 gallons per hour. The max flow rate of the pump is 95 gallons per hour. Since we did not have it at the max speed, we are within range. Now we will be covering Bernoulli's equation. We will be applying Bernoulli's equation at point A and point B. Point A will be the same point A as before at the top of where the water starts flowing, and point B will be our ground zero where the water starts flowing into our lake. Bernoulli's equation states that an increase in speed occurs simultaneously with a decrease in pressure. In simpler words, high pressure equals low velocity and low pressure equals high velocity. So as we look at our project, at point A, it's going to be a higher pressure, which is going to require a lower velocity, and in point B is going to be a lower pressure, which is going to be a higher velocity. It is also important to understand that we are making our calculations as if this was a 2D model, so that we're neglecting any losses, because in actual real life like this project, there would be some losses. With Bernoulli's equation provided to us, we're going to be plugging in all our unknowns, and we're going to be solving for V2. The velocity 2 is going to be the velocity at point B at the bottom at the stream. And if our calculations are done correctly, we will be having a V2 that is greater than V1. It is also important to remember that we already calculated V1, the velocity at point A, in the previous section where I talked to you about flow rate. The calculations are also up on the screen so that it makes it easier for you to follow along with me. So for P1 and P2, we're using 1 atm for both. For the density with rho, we're using 1,000 kilograms per meters cubed, and that is the density of water. For V1, we're using 0.66 meters per second. For height 1, since A is on the elevated side, that is 5 inches, which converts to 0.05 meters. Height 2 is going to be 0 meters. G is going to be our gravity, 9.81 meters per second. Now, as we apply all of these variables to our equation and we simplify for V2, towards the bottom, we're left with 1.4166 equals V2 squared. After squaring that, our second velocity, our velocity at point B, is going to be 1.19 meters per second. As we expected, our V2 is greater than our V1. And it is important for me to remind you that we are neglecting all losses. And for a little recap, our V2 has a lower pressure, and that is why it's traveling at a faster speed. versus at the top, since you can see that the water is coming out, there's more pressure in the top. That means that there's a lower velocity on the top. So if you have any other questions or are curious about the project or want a list of what it took to build it, please leave a comment down below and I'll make sure to answer that. And if y'all would like me to go into detail about the laminar flow at point A, make sure to leave a comment as well. Hope you have a great day.